Okay, then we can move with the next presentation. The next presentation will come from Buğra, Uğur, Yazıcı. The title is Hydrodynamic Optimization of a Submarine Forebody using Bezier Curve and Generic Algorithms. Yes, please. Buğra, Uğur, Yazıcı.
Thank you very much. Now I can't share my screen because Mr. Kırkbaş's screen is sharing. Okay. Mr. Kırkbaş, would you please close your session?
Okay. Sorry.
Yes. Okay, we see your screen.
Okay. Okay.
Thank you.
Good afternoon to all participants. This is Buğra, Uğur, Yazıcı speaking. First of all, I will thank you to organizing committee for their efforts and contributions for this valuable congress. I'm a senior submarine design engineer at STM Savunma Teknolojileri ve Mühendislik AŞ, working on the midlife upgrade project of Preveze class submarines of Turkish Navy. In addition to performing advanced engineering calculations, I am responsible for the structural integrity and layout optimization of various systems. As someone who thinks collaboration between academia and industry is the pillar of the sustainable future, I hold a master's degree in naval architecture and marine engineering. I am currently pursuing an academic career with a PhD in the same field at Istanbul Technical University. My research area primarily focuses on the optimization of hydrodynamic and maneuvering characteristics of submarine hull forms. Within this field, I am planning to specialize in the development of design environment that integrates different disciplines, including parametric design, optimization algorithms, reduced order modeling, and computational fluid dynamics. This presentation consists of 7 sections. And in the introduction section, brief information about submarine bow forms and the geometry will be presented. General outlook of the methodology is to explain developed platform for the optimization process. CFD method and the geometric definitions will be presented in the 3rd section. The formation of the geometry using Bezier curves will be explained shortly. Optimization process using deformed curves will be detailed, and finally, results and the conclusions will be shared. This submarine hull form can be divided into 3 main regions: forebody, parallel middle body, and the aft body. In this presentation, forebody of a submarine body will be of interest. The shape of the submarine forebody is one of the most important factors for low drag. Low drag means higher maximum speed and increased endurance, which means higher operational time for submarines. It is also associated with the positioning of acoustic sensors, torpedo tubes, and starting conditions for the flow around the hull. One of the main design criteria for the submarines is to ensure that the incoming laminar flow is transmitted along the submarine hull without being disturbed. In this way, it is aimed to prevent turbulent flow in the forepart where cylindrical sonar array is positioned, thus enabling the sonar to operate effectively. Even if blunt nose shape enabled designers to have more torpedo tubes, it was found that the blunt forebody shape resulting in extensive local adverse pressure gradient, and this becomes the basis for the circumfraction coefficient no longer decrease with an increase in flow velocity and remains constant after a critical velocity. This makes it possible for a blunt body of revolution to have 2 times more drag compared to a streamlined forebody. Bow form can also be associated with the stealthy characteristics of the submarines, since it has an important effect on the reflection properties of sonar waves that can be identified as target's echo strength. In the right-hand side, there are 2 different bow shapes of a submarine. Then these submarines are widely used in the navies outside. And the Assist class is a very well example for the target echo strength wise design. and Virginia class is a streamlined design and it has an elliptic bow. And Sorry class has also elliptic bow, but it has a different profile. In the present study, the Forebody drag optimization of a DARPA sub of AFF1 geometry has been investigated. 3D model of the bare hull form can be seen on the upper right corner of the slide. First, geometric definition of DARPA sub of AFF1 form modeled by using SalomeCAD software. Then computational analysis has been carried out by open source CFD software, OpenFOAM. Results have been validated with the experimental data using a mesh dependency study. Later, mesh deformation study using Bezier curves has been done to create optimization variants using the DARPA sub of curve equations. Then an optimization study has been carried out to find optimum hull form in the given design space and constraints. Finally, optimized bow form was compared with the well-known elliptical head forms, forebody forms in the capability of the optimization method has been evaluated. In this slide, the general outlook of the methodology platform will be presented. As you can see, Python is the core of the integration and process handling tasks. The whole platform is commenced with the Python code, and the design variables and the constraints are defined in the source code. Python code is also responsible for creating variance folders, integrating modules, and pass information between them. First of all, Python code initiates the optimization library, namely DApp, to have the parameters of the new variants. And these parameters then are sent to the curve deformation code, which is also natively written in Python and implementing Bezier curve-based deformation technique. Deformed and newly created bow form curve and other parts of the DARPA sub of AFF1 are returned then to the SalomeCAD. After this step, the SalomeCAD is activated in order to obtain parametric hull form, domain generation, patch naming, and exporting the domain with the hull geometry is done by Salome. And finally, exported domain, which is in STL format, is the input for CF Mesh library. Before starting optimization process, boundary condition, initial conditions, and solver settings of OpenFOAM is saved and used as a template files. Necessary amendments on the files are done by Python source code. The overall geometry in open source documents are issued by DARPA for two sub-of models, namely DTRS model No 5470 and 5471, and these are identical. Therefore, DRTC model 5470 is implemented in the study. The axis symmetric hull has an overall length of 4.536 meters and maximum diameter of 0.508 millimeters. Bow equation, parallel mid-body equation, and after-body equations are given respectively in this slide. The drag and analysis of a submarine form have been carried out with the state-of-art open source code CFD code OpenFOAM using run solver simple form, which is a steady state and turbulent incompressible flow solver. SSTK omega turbulence model is applied to simulate turbulent flow around the submarine. Second order upwind scheme has been selected for the momentum and turbulence terms, and a simple algorithm for the velocity pressure interaction has been selected. Dimensions of the computational domain is shown on the left-hand side, and the one on the right shows the boundary conditions imposed on the domain. The left and right sides of the computational domain have been defined as the velocity inlet and pressure outlet respectively. DARPA sub of hull has been defined as no slip wall to impose kinematic boundary condition. The surrounding surfaces denoted as far fields in the right figure have been defined as a symmetric plane. For drag analysis, unstructural hexahedral elements have been created around the hull. Open form extension CF mesh has been utilized in the grid generation process. Cartesian mesh algorithm has been used to generate the control volumes, and thus the fully hexahedral mesh structure has been obtained. Unstructural mesh around the DARPA sub-off hull is shown in the left-hand side figure, and the mesh size on the hull surface has been adjusted to keep Y+ values in an acceptable range. Average Y+ values of the submarine hull is around 4 for 3 meters per second velocity. After mesh dependency study, it can be seen in the table that the fine mesh around the hull is the most convenient mesh size, which is around 1 million cells. And in this study, a second-order parametric Bezier curve is implemented. And to define what is a Bezier curve, this is a parametric curve used in the computer graphics and related fields. The curves, which are related to Bernstein polynomials, are named after a French engineer, Pierre Bezier, who used it in the late 60s for designing curves and the bodywork of Renault cars. The equation for the formulation quadratic Bezier curve formulation can be seen in the slide, and these B0, B1, and B2 are the points of the Bezier curve. For explaining the formation process clearly, initial forebody of DARPA sub-off is plotted using 10 control points. It's the upmost or uppermost of the plots. And in the same manner, a Bezier curve using exactly the same first and last point of DARPA sub-off and the middle point, which has the coordinate of 1 in X direction and 0.5 in Y direction, is created also with 10 points. And as it can be observed with the blue dotted lines, X coordinates of the Bezier curve and initial DARPA sub-off forehead are not aligned with each other. Therefore, the first thing is to create a mapping function in order to make them aligned in the X coordinate system. After using a mapping system, one can easily observe that X coordinates of all points in the first and third plot are perfectly matched. The final step is to add delta values with respect to Y coordinates for the corresponding points of mapped Bezier curve to the initial curve. In this way, the position of the second control point of Bezier curve is changed and the curvature of forebody is altered, as it can be seen in the bottom of the plots. And after that, since the CFD simulations took a lot of time for the optimization process, in order not to create geometrically inappropriate designs after deformation, it is necessary to check the control points of the new deformed curve. In this way, it's prevented to obtain values larger than the breadth of the initial form, and this forms geometrically inappropriate because that concludes in manifold geometry whose any y values is less than 0. A function using Sobol algorithm has been created to determine the limits of the variable y to be used in the optimization algorithm. This function returns 0 if the curve is violated the geometrical constraints, and 1 if the curve is feasible. Curve control analysis was performed on a 100 by 100 even-spaced grid and presented in the right-hand side figure. Sobol algorithm is a space-filler figure, as you can see in the left-hand side. And by using this Sobol algorithm, it can be easily concluded that y values should lie between -1.6 and 0.05 so as to have feasible designs, as in the right-hand side of this presentation. And the optimization process, the open source DAP library has been utilized when creating an instance of a genetic algorithm in order for variant parameters to be meaningful, but bitwise mutation is blocked. Parameters for crossover probability and the mutation probability were taken as 1, and it's observed that when these parameters are relatively low, same variants created in the populations which are diminishing overall performance of the optimization process and increasing the total computational time. Selected algorithm is defined as NSGA2. In the NSGA2 algorithm, the population evolutionary strategy can be concluded as according to the fast non-dominating sorting strategy to determine each individual's non-dominated level. The total number of 15 generations have been created. Each consists of 10 individuals as population. Therefore, 150 variants created and analyzed in the optimization process. Coordinates of
Can you speed up, please?
Okay. The total direct of the optimized hull form, which is the 114th variant of the design, is the optimum one, and the design is as it can be seen in the slide, is reduced as 7.32%. And on the left side, pressure distribution of the initial hull is the upper left-hand side, and the optimum hull lower can be found. And it can be noted that the negative pressure contours have abrupt change in and more in length for the initial hull as compared with the optimized hull. Pressure distribution on the forebody section of the initial hull is changing rapidly. However, optimized hull has more smooth transition and pressure does not drop significantly in the nose section. Velocity distribution has the same trend when comparing the pressure of the forms. It can be easily observed that velocities are equal to inlet velocity reach out for the optimized hull in the middle section more than the initial one. On the right-hand side figure, Q criterion with vorticity contour is shown. Vorticities are dramatically reduced in the forebody section of the optimum hull as compared to the initial hull. And this figure shows the best individuals among the generations almost coincide with the optimal streamline shape that can be defined as Munesun suggests. And using elliptical form equation, Munesun find that optimum shapes for the resistance characteristics have value of NF around 1.15, as you can see in the red green dots in the plot. And the optimum form that has been found in this present study can be is shown as an orange line. Conclusions of this present study is the cubic Bezier curves can be implemented within the deformation phase. Adding extra control points to the deformer curve may increase the complexity of the process, and unfeasible type of generated variance may be observed. For constant parallel mid-body and off-body curves, parameterization of a forebody curve has been realized just using two parameters. Therefore, the complexity of the system is very low, which causes genetic algorithm to find best variance easily, even if unfeasible geometric constraints enforced to be used within the optimization loop. Genetic algorithm that implements NSGA2 selection algorithm has been employed to find optimum forebody hull shape. Bitwise mutation and method of the algorithm is cancelled out to have design variables of newly generated hull forms to be restrained. In this way, consistent and robust design space have been obtained. 7.32% drag reduction has been achieved by the genetic algorithm, keeping the total forebody length and maximum hull diameter as constant and equal to DARPA SOBOP AFF1, and each simulation took almost 8.5 minutes with the presented core. Thank you very much for your attention. If you have any questions and comments, I would like to answer them.
Thank you very much, Mr. Yazıcı. Another very interesting topic and very interesting presentation. Thank you very much. And now we can take questions or comments.
I have a comment about the study, if you permit me to talk. Thank you for the presentation, Buğra. I have a comment about it. So there, as far as I can understand, there's a trade-off. This is a single constraint optimization, right? You take the total resistance as the integral variable here.
Yes.
Yeah. Okay. So I think a better study would also include. So there must be ship design is a process of trade-off. So if we are gaining something from somewhere, we have to be losing something from another place. So, for example, are we losing some sea-keeping abilities or maneuvering abilities of the ship? A better study, I think, would include some sea-keeping or maneuvering analysis of the original and the optimized forms. I mean, in my opinion, I can see that we are also losing some space, some displacement, right?
Yes.
Or so you may also think of keeping the displacement constant when optimizing your form.
You are 100% right, sir. And I have another work and study for implementing the multi-objective optimization, keeping into account the volume and prismatic coefficients and some other parameters that affects the overall performance of the submarine hull forms. But in this study, what I am trying to implement is to have a partially parametric design using just two variables, that is the coordinates of the Bezier curve. This is the main idea behind this study, but you are right, and I am trying to implement what you suggest in your comments.
Thank you. Thanks.
Thank you very much. Are there any questions or comments about the study?
Thank you very much. It was very impressive.
Thank you.
Thank you very much.
Okay, so I believe there are no more questions, and maybe we are just going to wrap up the session then. If there is nothing more, I mean, any comments or anything else? Nothing. Okay, so then thank you for all the participants, and we are just closing the session then. Yeah, have a good day.